Hello, dear students. Glad to meet you again in this session. In this session 2.7, we are going to discuss quantum mechanical model of the atom from chapter 2, structure of atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 2.1, we have discussed the discovery of subatomic particles and its characteristics. In session 2.2, we have discussed the atomic model, that is J.J. Thomson atomic model and Rutherford atomic model and its drawbacks. In session 2.3, we have discussed the dual nature of electromagnetic radiation. In session 2.4, under the concept atomic spectra, we have discussed continuous spectrum, emission spectrum, absorption spectrum, atomic spectrum, and line spectrum of hydrogen. In session 2.5, under the concept Bohr's atom model, we have discussed postulates and explanation of Bohr's atom model for hydrogen atom, explanation about the line spectrum of hydrogen atom, and limitations of Bohr's model. In session 2.6, we have discussed two important developments, that is de Broglie's relationship and Heisenberg's uncertainty principle, which leads towards the quantum mechanical model of an atom. Learning outcomes. Students, at the end of this session, you will be able to define mechanics and quantum mechanics, differentiate classical and quantum mechanics, describe Schrodinger wave equation for the behavior of an electron in an atom, explain hydrogen atom and Schrodinger equation, list the significance of the Greek word psi, which represents wave function, and list the important features of the quantum mechanical model of an atom. Before getting into quantum mechanical model of atom, let us recall the Newton's law of motion, which are the basic laws for the motion of an object. The motion of objects that we come across in our daily life can be well described by classical mechanics, which is based on Newton's law of motion. Newton's first law: an object at rest stays at rest, and an object in motion stays in motion unless it is acted upon by an unbalanced force. Newton's second law of motion: acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. Consider these two pictures. When 20 units of force is applied to pull the wagon moves comparatively fast. That is, the acceleration is greater when compared to the acceleration when we apply 10 units of force to pull the same wagon. So, acceleration is directly proportional to the applied force. Consider this picture. When we apply the same 20 units of force to pull the wagon of heavy mass, the acceleration is comparatively slow. So, greater applied force is required if the mass of the wagon increases. This shows that acceleration is inversely proportional to mass. By combining the equation 1 and 2, we get acceleration A is directly proportional to F and inversely proportional to M. We can write this equation as M into A is equal to F, which gives F is equal to M into A, which is Newton's second law of motion. Here in this picture, you could see engine pushes the aircraft in the forward direction, that is the action, and the exhaust flow pushes the aircraft in the backward reaction, that is the reaction. This is the Newton's third law of motion, that is every action has an equal and opposite reaction. The motion of the objects that we come across in our daily life can be well explained by using classical mechanics, which is based on Newton's law of motion. First, let us see the definition of mechanics. It is a branch of science which deals with the study of the physical state of bodies at rest and in motion under the action of forces. Classical mechanics successfully describe the motion of all macroscopic objects like falling stones, orbiting planets, etc., based on Newton's law of motion. In earlier days, classical mechanics was also called Newtonian mechanics. This classical mechanics predict the future state of the system based on the force acting on it if its position and momentum is known. For example, when you know the position and momentum of the ball, when you kick the ball, based on the force you acted on it, we can predict the future state of the system, that is the future state of the ball based on the force acting on it. For macroscopic objects that are not extremely massive but have predominantly particle character and its speed not approaching the speed of light, then classical mechanics gives the accurate results for that macroscopic objects. Drawbacks of classical mechanics. Classical mechanics fails when applied to microscopic objects like electrons, atoms, and molecules. It ignores the concept of dual behavior of matter, which is significant for microscopic particles, and the uncertainty principle. So, this leads to the next concept called quantum mechanics. Quantum mechanics. Microscopic objects such as electrons has both observable wave-like and particle-like properties. To explain the behavior of electrons and other microscopic particles, a new branch of science called quantum mechanics was developed. Quantum mechanics is a theoretical science that takes into account the dual nature of matter. Based on quantum mechanics, a new model of atom was developed in the earlier years of 1920s. The concept of uncertainty principle proposed by Heisenberg and the dual nature of matter proposed by de Broglie leads to the development of quantum mechanics. Quantum mechanics was developed independently by Werner Heisenberg and Erwin Schrödinger in 1926. Quantum mechanics is based on the ideas of wave motion of electron. The fundamental equation of quantum mechanics was developed by Schrödinger and it won Nobel Prize in 1933. The time-independent Schrödinger equation can be expressed as H cap psi is equal to E psi, where H cap is a mathematical operator known as Hamiltonian operator and psi is the wave function and E is the energy of the system. This above equation can be solved only for certain values of E, the total energy. Now, let us see what is the total energy of the system. The total energy of the system E is equal to the kinetic energy of all the subatomic particles, that is electrons and nuclei. Inside the nuclei, it consists of protons and neutrons, right? And we know that electrons revolve around the nuclei and there exists a kinetic energy. And inside the nuclei, neutrons and protons will vibrate and there exists a kinetic energy. So, the total energy of the system E is equal to the kinetic energy of all the subatomic particles and the attractive potential between the electron and the nuclei and the repulsive potential between the electrons and the nuclei individually. The Hamiltonian operator H cap is equal to minus H square upon 8 pi square m into dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus v. This derivation you will be learning in the higher classes. Substituting the value of H cap in the below equation, we know that this equation is a time-independent Schrodinger wave equation. So by substituting the value of H cap in this equation, we get minus H square upon 8 pi square m into dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus v into psi is equal to E into psi. Multiplying the above equation by minus 8 pi square m upon h square and rearranging the above equation, we get dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m upon h square into e minus v psi is equal to 0. This is the Schrodinger wave equation in terms of differential equation. So this equation incorporates the wave-particle duality of matter as proposed by de Broglie. This Schrodinger wave equation describes the behavior of an electron in an atom. In this equation, x, y, and z are the three space coordinate. M is the mass of the electron, H is the Planck's constant, E is the energy of the system, V is the potential energy of the electron, and the Greek word psi wave function is the amplitude of the electron. So we know that Erwin Schrödinger expressed the wave nature of electron in terms of differential equation as dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m upon h square into e minus v into psi is equal to 0. This equation determines the change in the wave function in space depending on the field of force in which the electron moves. For example, the wave function psi for an electron which moves in the field of force in which the energy level n equal to phi varies with the wave function psi of an electron which moves in the field of force of energy level n equal to 1. The solution of Schrodinger wave equation are known as wave function. In an atom or molecule, only specific energy states are permitted, and this permitted total energy values are called eigenvalues, and the corresponding wave function. For example, for n equal to 1, we have the wave function psi 1. For n equal to 4, we have the wave function psi 4. And the corresponding wave function represents the orbital. In case of atom, we call it as atomic orbital, and in the case of molecule, we call it as a molecular orbital. When Schrodinger wave equation is solved for hydrogen atom, several wave functions are obtained. Out of this, only certain wave functions are permitted. These wave functions corresponds to a definite energy level, and we know that this is called orbital. Each permitted wave function corresponds to a definite energy levels, and the quantized energy levels that an electron can occupy for hydrogen atom and the corresponding wave equation while solving the Schrodinger wave equation for hydrogen atom are characterized by sets of three quantum numbers. Principal quantum number which represents the size of the orbital, azimuthal quantum number which represents the shape of the orbital, and magnetic quantum number which represents the orientation of the orbital, which we will be discussed in the later part of this chapter. When an electron is in any energy state, for example, whether it is n equal to 1 or n equal to 3 or so on like this, the wave function corresponding to that energy state contains all information about the electron, and the wave function is a mathematical function whose value depends upon the coordinates of the electron. The wave functions of hydrogen or hydrogen-like species. Why we call it as hydrogen-like species? We know that the atomic number of helium is 2. So it should have 2 electrons. When it loses 1 electron, then it will become He plus ion. So it will have only 1 electron as that of hydrogen. Coming to lithium, we know that the atomic number of lithium is 3. So it should have 3 electrons, right? But when it loses 2 electrons, it will become lithium plus 2, and it has only 1 electron as that of hydrogen. So the wave functions of hydrogen or hydrogen-like species like helium plus ion and lithium plus 2 ion with 1 electron are called atomic orbitals. Such wave functions pertain means related to one electron species or called one electron system. Schrodinger wave equation gives the probability of finding an electron at a point within an atom, which is proportional to the square of the amplitude of the wave function psi square at that point. So psi square is equal to probability density and it is always positive. We will discuss the concept, the probability density, which is equal to the square of the amplitude while discussing the significance of the wave function. The quantum mechanics results of the hydrogen atom successfully predict all the aspects of hydrogen atom spectrum, including some phenomena that could not be explained by Bohr's model. We know that Bohr's model could not explain the spectra of atoms and he could not explain the phenomena of Zeeman effect and Stark effect, and he ignored the dual character of electron. Schrodinger equation cannot be solved exactly for multi-electron atom. This difficulty can be overcome by using approximate method. Such calculations with the aid of modern computers show that the orbitals in atoms other than hydrogen do not differ in any radical way. That means do not differ in a very different way from hydrogen orbitals. But the principal difference lies in the consequence of increase in the nuclear charge. Consequence means as a result of increase in the nuclear charge. We know that if the atomic number increases, then the number of electrons and the number of protons also increases, because we know that atomic number is equal to number of electrons or number of protons. If there is an increase in the number of protons in the nucleus, obviously it has the greater tendency to attract the electrons in the orbit towards itself. So the orbits are somewhat shrink or it gets contracted. The energies of hydrogen and hydrogen-like species depend only on the principal quantum number n. Why? Because hydrogen and hydrogen-like species contains only one electron. So the electrostatic interaction is between the positively charged nucleus and the negatively charged electron. So here the energy depends only on principal quantum number. But in the case of multi-electrons like carbon or oxygen, the energies of the orbitals in the multi-electron atoms depend on principal quantum number and azimuthal quantum number. Because in the case of multi-electron atoms, along with the attraction between the positively charged nucleus and the electron, they also possess electron-electron repulsion. Thus, the energy depends both on principal quantum number n and the azimuthal quantum number L. Now let us see the significance of the Greek word psi, which represents the wave function. We know that a moving electron is associated with a wave, and the wave function psi gives the amplitude of an electron wave. But psi has no physical significance like shape or size. However, the square of the amplitude of an electron wave psi square has a physical significance. We can understand this concept by recalling the electromagnetic radiation. In electromagnetic radiation, we know that the intensity I is equal to half epsilon naught E naught square into C, where epsilon naught is the permittivity of free space, E naught is the amplitude of the electric field, and C is the speed of light. So from this equation, it is very clear that the intensity is directly proportional to the amplitude, right? In the same way, the square of the wave function psi, that is the square of the amplitude, gives the intensity of the electron at a particular point. This psi square helps to access the probability of electron in a particular region. So psi square is called probability density and psi is called the probability amplitude. So the square of the amplitude gives the intensity of the electron. Now let us list out the main features of quantum mechanical model of atom. First, the energy of the electron in atoms is quantized. That means the electrons can have only certain values. Next, the existence of quantized electronic energy levels is a direct consequence, that is the direct results of the wave-like properties of electrons. That is why when Schrodinger equation is solved for hydrogen atom, even though we obtain many solutions, only certain solutions are allowed. That is why when Schrodinger equation is solved for hydrogen atom, even though we obtain many solutions, only certain solutions are allowed. Thus, the discontinuous electron waves are not allowed, only the continuous waves are allowed. According to Heisenberg's uncertainty principle, the exact position and the momentum of an electron cannot be determined with absolute accuracy. As a consequence, quantum mechanics introduced the concept of orbitals. That is why we consider the probability of finding the electron at different position in an atom. An atomic orbital is the wave function for an electron in an atom. The atomic orbital, that is the wave function, is associated with definite amount of energy. Since many wave functions psi are possible for an electron in an atom, there are many atomic orbitals. An orbital cannot contain more than 2 electrons. It can contain a maximum of 2 electrons. And all the information about the electron in an atom can be obtained from the orbital wave function. The probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function psi square at that point. Psi square is also known as the probability density and is always positive. Students, now let's recall all the topics that we have discussed in this session. We have discussed mechanics and quantum mechanics. We have discussed the difference between classical and quantum mechanics. We have discussed Schrodinger wave equation for the behavior of electron in an atom. We have discussed hydrogen atom and Schrodinger equation. We have discussed the significance of the wave function psi. And we have listed the important features of the quantum mechanical model of atom. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.